like being on the video camera because they're here. Okay, this is my boy Haley. Hey Haley. She's like, okay. This is my new lavalier mic. I hope this sounds good because I bet it will. We're gonna talk today. Let's write down our objective. You notice a while ago I started putting standards up there. I don't know if you've ever read them. Those are for your benefit. These are the standards that are being met by your education here. The objective is diagram and describe the magnetic force. Let's change it a little bit. I'm going to put diagram and describe field forces. So let's put that down. Diagram, Hunter, and describe, Gunner, field forces. Let's talk about garbage. The stink field. Someone did their homework.
Yeah, I looked at the lesson over.
Good. And that's it?
That's really cool. No, I did the rest. That's really cool that you can write like that.
Oh, I'm a graffiti. That is graffiti. Okay. So the title of the lesson is garbage. Why are we talking about garbage here in science today? Alla Owens just took. I used to have a little 3D printed garbage can over there. It said waste management on it. Have you guys ever encountered a dumpster?
I saw it. Yeah.
Raise your hand if you've seen a dumpster. Raise your hand if you know some people who are hot garbage. Yeah, keep them up. Yeah, what? Shh, listen. Oh, good. So, let's think about, let's close your eyes, let's do a little thought experiment. Imagine, Ty, the instructions were, close your eyes. Close your eyes. We're doing a little thought experiment, which necessitates your eyes being closed. Now imagine it's July. You know the month of July. And it's 105 degrees. And it's the 4th of July parade. And you're having a 4th of July party at your house. Okay, keep the imagination going. Ethan, we're trying to imagine some stuff here, and you're wrecking it for everyone. Close your eyes. It's a 4th of July party. And your mom says, oh no, insert 8th grader name here. Oh no, Taylor. Oh no, I accidentally threw away the hot dogs this morning. Would you look at how the dumpster? And so you wander over to the garbage can, and there are the hot dogs in the bottom of the dumpster. And you notice odor of dumpster trash. Can you smell the odor? And then as you get closer, what happens? Raise your hand if you know. As you get closer, what happens to the magnitude of the stench? Kendall, explain what happens to the magnitude of the stench. Good. Now open your, well, no, what do you mean? As what? As you're, where are you walking to? You're walking to the garbage, and as you're walking toward the garbage, the stench gets, the stench gets stronger. So open your eyes now. Now look, here, someone left the thing open. I hate that when people do that, but someone left the thing open. Here's the hot garbage in there, and there are the hot dogs. They slid down the side. And then, and the bottom is always rusted, and there's just some garbage pooling out of it. You know this. You know, you guys know the dumpsters that I'm talking about? Yeah. And there's a hole always in the bottom, and like cats climb in there. There are rats here, but there are cats. And there's just you think, Mom, instead of grabbing the hot dogs, I'm going to just grab her a cup of hot trash juice. No, you don't do that. But as you get closer, so there's a what we might call a stink field emanating from the garbage can. And as we get closer, here's the interesting thing about fields is that as we get closer, here's you at time equals 0. Here's you at time equals 1. Here's you at time equals 2. And here's you at time equals 3. Let's also have a distance. Let's say in meters, and here you're 0 meters, you're in the trash juice. Here you're 1 meter. Here you're 2 meters. And here you're 3 meters away. That's supposed to be incremental. Okay? So far so good, right? And then let's think of a unit to measure stench coming into our nostrils. Just a unit. Yes, Gunnar. Thank you for raising your hand. What would be a good name for a unit to measure the amount of stench? There isn't an official one because that's a subjective thing. But let's think of a cool name for measuring trash stench. Nostips. Okay, good. No, he said nostips and he meant it. What's the abbreviation for nostips?
NPS.
Okay, NS. So we have nostips. So now here's what's interesting. If we are on this, let's think about what is the magnitude maybe of the in nostips. What is the amount of trash smell we're getting? First of all, can we ever be in the literal exact same place as the trash juice?
Yes.
No. Can it occupy the same space as you?
Yes.
No. What? No, it can't. You can touch it, but you can't be in literally the same spot of the universe. You might be, even if you're touching the trash juice, it's getting all over you. Even if you eat it, it's not touching the part of you that makes you up. So we'll say almost 0. How many nostips here?
0. Almost 0.
No. How many nostips? How much smell is there?
Oh, 100. Let's say 5.
Infinite. We'll say it's infinite. Infinite nostips. This is the smelliest thing that can ever exist. As we get away from it, this reduces by the inverse square. So let's say it'll be easier with this one. At 1 meter away, we're having 1 out of 1 nostips. Here, instead of having 1/2 the nostips, we have 1/4. Here we have 1/9. You see what's happening? The bottom is reducing not by how far away we are, but by how far away we are what? What mathematical operation? How far away we are, what?
Nostips.
Yeah, how far away we are in nostips. So we have, but it's not half as strong when we're twice.
It's times by so 2 times 2.
That's squared. What it is, we call this the inverse, write this down please. This is the real science connection. Inverse square law. What's the word inverse mean? We're talking about a what? A what? Yeah, it's the flip. The fraction is flipped over x. And then squared means, what mathematical operation does square mean? Yeah, to the second power. So if we have, so thing y is related to thing x by the 1 over x squared. The further away we get, usually we represent it this way. It's usually 1 over d squared equals, what kind of thing are we measuring here? Stench? Stench equals 1 over the distance away we are squared. So as we get further away, the stench decreases, but not just linearly. It doesn't decrease 1 for 1. It decreases as the inverse square. So if we get 4 times farther away, the stench is what strength?
Times 4.
No.
To the 4.
No. 1 over 4 squared. So 1/16 is strong. If we get 5 times as far away, it's 1/25. 6 times as far away, 1/36. Right? So it's a fraction, but the thing's squared, not just a fraction. So the inverse square. The example I kind of like, this is a good example. I like this example. Garbage. Hot, juicy garbage. This is a good example, but the physics book that I teach out of uses the example of a butter cannon. So if we the idea is, I'm going to leave inverse square up because that's the actual science connection here. There is science in garbage, I guess. Sometimes science is garbage. The example that the physics book uses is called the butter cannon. So there's this butter cannon. It shoots, can you guess what it shoots? Butter.
Oil.
Butter. And when it's 1 meter away, it'll butter, I don't know what that's supposed to be. It's supposed to be toast. It'll butter 1 piece of toast. So 1 meter away, it'll butter 1 piece of toast. Let me do it sideways. 1 piece of toast. If we double how far away it is, will it butter 2 pieces of toast? No, it butters 4 pieces of toast. If it's 3 times as far away, 9 pieces of toast. 4 times as far away. Okay, now check this out. I don't know if you realize about math, but the reason we call to the second power squared, you've heard that before, I've just said it, is that, look, we doubled what about this? Just the what?
Square.
Just the length, or the width. It doesn't really matter because this is square. But if we double the length, what happens to the area? Multiplies by 4. So length. What's the area though? 4. Here we have the width is 3. So the area is 9. Here the area is, or the width is 4. So the area is, and what shape does that make? a square. That's why we call it squared. I don't know if you ever realized it, but that's why we call it to the second power squared, because if we increase the length of the side by this amount, the area of the square increases this amount. Butter cannon. 1 toast. 4 toasts can be buttered at 2 meters, but what happens to the thickness of the butter? If we're using the same amount of butter every time, it gets less. So we have inverse squared amount of butter. So we have a quarter as much butter on this one. Okay, let's put amount of butter. 1. 1/4 as much butter per piece of toast, or thickness of butter. How much butter per toast on this one? 1/9 as much. And on this one? 1/16 as much. How does this all relate to forces? Well, these pertain to what kind of forces? Nostips. Yeah, what kind of forces, though, specifically? Field forces. Yeah, these apply to any field force. And unlike the butter, but yes, like the garbage can, these happen in 3 dimensions. Force fields are always 3-dimensional.
How would they be
So 2-dimensional is like on the whiteboard. I'm drawing them 2-dimensional as a circle. They go out as a circle. Yeah, not technically, but representing them 2-dimensionally on the board as a circle. And so in real life, they'd be a sphere. They'd come out. So like if there were a literal piece of trash here, no, I was gonna make a mean joke. Never mind. If there were a literal piece of trash here, it wouldn't just be this far away and this far away that I smell the trash 1/4 as much. It would be out here too, out away from the board too, and inside the board, etc. Yes. Oh, good. That way the school can save money on corn dogs. Yes.
I'd say that if you want the perfect layer of butter.
Okay, where would you put it for the butter cannon? You'd have this, because this is just too much butter. You're going to clog your arteries up. Too much butter. This is still a little too much. But this one, you might as well just eat.
Yeah.
Okay. Anyway, so what are some examples of force fields? No, okay, that's not a real force, though. Gravity, magnetism, in fact, the strong force and the weak force, all the 4 fundamental forces of the universe are field forces, meaning they exist in 3 dimensions and they decrease the further away they get from their source. Let's draw, how would a gravitational field look? Here's a celestial body. We'll say Earth. Here's planet Earth.
Is that little one?
No, this is supposed to be South America. It's abstract. Be quiet. Anyway, this is. Oh, I need to start asking you guys to. I need to say your questions when you ask them because the mic cannot hear your voices anymore. Ask me a question, Dalton.
How big is the Earth around?
There, that's a good question, and we won't be able to hear it all. What Dalton asked is what I have to do. Dalton said, "How big is the Earth around?" I don't know. I think the radius of the Earth is 6,400 kilometers. I think so. How big around would be that times 2 pi.
What about the magnet or the?
Yeah, we're gonna get there in a second. But first, let's draw the gravitational field around planet Earth. What's true about gravity as opposed to magnetism? You remember we said yesterday that gravity is always Ty, whereas magnetism can be either or Ty, what is gravity always? Yes, that's true. You're gonna kick yourself because you were mentioning this yesterday. What is gravity always, Gunnar?
Gravity is always pushing.
No, gravity is always the opposite of that. Gravity is always, always attractive.
And then attractive and repulsive.
Gravity is always attractive. Magnetism, right? Magnetism, and therefore electricity. Electromagnetism is what we call it. Electromagnetism is attractive and repulsive. Remember, charges, positive and positive, do what? No.
Or no, repel. Sorry.
Repel. Negative and negative? Repel. Negative and positive? Attract. Opposites attract. This is the worst handwriting I've ever had. But gravity is always attractive. So what would the gravitational field around Earth look like? Fate?
It would look like
Yeah, always going towards it. Arrow's always going towards it. It always attracts, by the way, everything else in the entire universe. How come we don't notice the attraction of the Andromeda galaxy, which is hundreds of thousands of light years away, to Earth? Yeah, it's farther away because it decreases. The gravitational force decreases as the distance squared. So the further away something is, eventually, it never gets to zero. It's something in math that's called an asymptote. Have you heard of an asymptote? It's where something, if we graph the distance over here, distance on this axis, and the strength on this axis, the further away we get, what happens to the strength? It weakens. So if we're at 0, it's infinite. If we're at 1, it might be up here. If we're at 2, here, 3, here, 4, 4, etc. What shape does it make? Well, it makes a curve like that. But it never, ever, 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 ever gets to 0. Because we're talking about the bottom number of a fraction here. So if it's at 1, it's 1 over 1. If it's at 2, it's 1 over 4. 3, 1 over 9, etc. Can we ever have it be 1 over 0? What happens if we divide by 0? You can't. The universe breaks down. That's why this asymptote exists. So technically, everything in the universe attracts everything else because the force is never 0. But it does pretty quickly get so small that it can't actually cause any motion. Yes, Fate. Asymptote. A-S-Y-M-P-T-O-T, which is just what we call it in math, where what's the word Mr. Snelly would want me to use? A quantity. No, a function. That would be better. Ooh, that sounds like math. A function approaches 0, but never reaches it. It can get to be 1 over 999 billion, or 1 over 999 billion, or 1 over 10 to the 30th, but it's never 0. Gravity? What else might that be true for? Just extrapolating, Gunnar. What else might that be true for? Well, what other force might it be true for? If it's true for gravity, technically everything affects everything. Also, it's probably true for magnetism. The magnet that we used in the lab yesterday is technically gravitationally attracted to a magnet in the hand of an alien light years away that don't exist yet or might not ever exist. Yeah, technically. Yep. In the entire universe. But how close do they have to be for them to actually cause a change in motion, to cause an acceleration? Really quite close. Even a very strong magnet. You remember, if I held that very strong magnet that I had that one day, even half a meter away from the board, it wouldn't ever reach the board because the force wouldn't be strong enough. I had to hold it fairly close. Even a very strong magnet, I had to hold very close, fairly close to get it to attract to the board. Yes? Oh yeah, actually, the question was, can we make a living thing magnetic? Yeah, actually, if we have, I forget exactly how this worked, but we made a frog, not me. Some scientists had a super cooled magnet, and they were able to generate an enormous magnetic field. We measured magnetic field strength in a unit called Teslas, and it was hundreds or maybe even tens of thousands of Teslas, and they were able to make this frog float in it. Actually, anything that has water, remember, the electrostatic force with the balloon thing attracted that water stream in that video, and you couldn't really get to work in the lab. But if you have water in you, you are technically magnetically attracted to anything that's exhibiting static force. But usually it's just so weak that it doesn't move anything. But they could make this frog levitate on a magnet, which was pretty dang cool. Anyway, now let's draw the electromagnetic field around Earth. How will it look different since electromagnetism is both attractive and repulsive? First of all, it will have what's, just like a magnet. Yes? Yeah, Gunnar says poles. It'll have poles just like a magnet. What do we call the poles of planet Earth? North and south. And so it ends up looking like a magnet. Remember, we drew the magnetic field line, so it looks like this. Okay? Does that make sense? Just like a magnetic field has these lines. Except, what's one problem with this model? What's one shortcoming of my model? It should be what, Gunnar? How can you always...
Way bigger.
Yeah, it should be way bigger, obviously. There's a scale problem. What else, Fate? It has to be three-dimensional. That's what Gunnar said, too, just for the record, but he's answered so many questions. Now, the other thing that's different about this model is that in reality, there's a huge source of electromagnetic radiation nearby. What do we call that guy? The sun. There's a big old sun over here, and he's emitting charged particles all the time, and those cause the magnetic field of planet Earth to actually look more like squished up on this side and then trailing out on this side, which makes it a lot prettier.
Wait, can I ask you a question?
Yeah, because all these things are being emanated, and they're squishing this side and then swooping out this side. So whichever side of planet Earth is facing the sun has a squished up magnetic field, and whichever side is away from it has this swooped out thing.
Don't solar flares affect the electric
Yeah.
magnetic?
In fact, the sun has its own magnetic field too, and the reason solar flares exist is that the sun, instead of having two, which Earth technically doesn't just have two magnetic poles, the domains aren't always lined up perfectly. If they were, it would be a super strong magnet. We'd probably be squished just by the magnetic force, like that frog was made to levitate. But because of that, there's also multiple bajillions of poles. Like each little tiny magnet that we have, like on your fridge, is changing magnetic field of planet Earth a little bit. But the sun has hundreds of thousands of magnetic poles that are really quite strong. And when some of those shift, almost entirely hydrogen. But when those magnetic fields shift, they can cause a snappage. It's not really a physical snap like a rubber band, but if you think of things like rubber bands, when they move and twist, they can sometimes snap and switch poles, and that causes on the sun.
average solar flare is like the size of an acre or something, right?
I don't know about the average, but I know they can be very large, yeah. Let me see if there's anything else that we specifically need to talk about. The main things I want you to know are that fields are three-dimensional. Yes? Fields are three-dimensional. They decrease in strength the further away you get, but not just by any relationship. They decrease by the inverse square. And that gravitational fields are always attractive, whereas magnetic fields can be attractive or repulsive, and so they have different shapes. Fate. All that is the same as a bar magnet with north and south. It's like north and south, and then they just bend it. So now north is here and south is here. And what that's useful for in a horseshoe magnet is that you can really pretty much, for an object that doesn't have its own magnetic poles already, you can pretty much generate twice the magnetic force with only that. Because, for instance, like a nail or a paper clip that doesn't have its own magnetic poles will be just as attracted to the south pole of a magnet as the north pole. And so that magnet, the horseshoe magnet, now since both are facing the same way, can attract something twice as heavy, for instance, for the same size magnet. Does anyone else have questions? There's a cool little thing about ferrofluid in here that I wish you would read. I have some ferrofluid that we could mess. In fact, that's what we were going to use yesterday, but you guys used so much of your time. Yeah, there's ferrofluid's really cool. I would read the little engineer it tab about ferrofluid. Other questions? When's the quiz? Tomorrow.